Hi, everyone. Today we're going to talk about recoil. This is one of the interactions in momentum that can actually be conservative. We have an archer of mass 60 kilograms, stands on frictionless ice and fires a 0.030 kilogram arrow with a flat trajectory with an initial velocity of 85 meters per second. Number 1 asks, find the velocity of the archer after firing the arrow, and it says to use momentum. Number 2, we'll talk about why force and energy methods don't work here. And then we'll talk about if this is impulse, recoil, or collision, and then does conservation of momentum apply. So first, let's get our givens. I'll write them off to the side. We have mass 1, we'll call the archer number 1 is 60 kilograms. Mass of the arrow is 0.03 kilograms, and the velocity of the arrow is a whopping 85 meters per second, and we want V1. So to set up this equation, in this scenario, right, they start off not moving, and then they suddenly start moving. You get M1 V1 plus M2 V2. Now, if you want to solve for V1, you would subtract M2 V2 and divide by M1 to get that velocity. So we're going to take the negative momentum of the arrow and divide by the mass of the archer. What are the masses? We got 0.03 times 85 divided by 60. That will give you V1. And if you put that in your calculator, you get negative 0.0425 meters per second. And the reason that velocity is negative is to show direction, right? We're going to say the arrow is moving forward. That's positive. Archer goes backwards. That would be negative. So not moving very fast, but this archer is actually moving. Now, it said use momentum. Why would force or energy methods not work here? So let's look first at force. Okay, if we have, it's a Newton's third law of pair, right? Every action has an equal and opposite reaction. As shown here, fire an arrow, the arrow pushes back on you. So we have third law of pair, right? F1 would equal negative F2, right? So if we have M1 A1 would equal M2 A2. So say this is the math, same ones and twos. Mass of the archer times the acceleration of archer equals mass of the arrow times the acceleration of the arrow. This we can't solve for, right? Because we don't know the acceleration. We don't know how long it took that arrow to get to 85 meters per second, or how long it took the archer to accelerate to negative 0.0425 meters per second. So we don't have time. If we had the time, then we could calculate acceleration. Or if it was just given to us, then we would be able to solve that. Okay. Next, energy, right? Energy methods. So if we do a COE, okay, conservation of energy, they start off not moving, okay, so we'll call that 0, and then they suddenly have kinetic energy 1 and kinetic energy 2, meaning that, how did I do it before? I did negative 2. Okay, so we'll do negative kinetic energy of the arrow equals the kinetic energy of the archer. So let's see if this is true. We have negative 1/2 M2 V2 squared equals 1/2 M1 V1 squared. If we have M2, let's see, we have negative 1/2. Actually, those 1/2s can go away, right? Just divide by that 1/2 on both sides, get rid of that. So then we have negative M2, that was 0.03 times 85 squared equals 60 times 0.0425 squared. Now, just looking at that, we can see that that's probably not going to be equal. And if you put that in your calculator, you get negative 216.75 for the left and 0.1084 for the right. Obviously, those do not equal each other. So what we're missing here, it's not that the kinetic energy isn't conserved or energy isn't conserved. What we're missing here is the initial energies, okay? There is not just zero initial energy. There is actually some potential energy in the bowstring that we don't know about, right? If we knew the potential energy of a bowstring, I have no idea what that equation would be, but if we had it, then it's possible that we could do some kind of conservation of energy in this scenario. But since we don't have time and we don't have the potential energy of the bow, we can't use those methods, right? So that's why those don't work here. Now, is this an example of impulse, recoil, or collision? We can quickly say this is not collision, right? You can also quickly say this is recoil because the teacher said so. I keep saying recoil over and over and over again. But why is this not impulse, right? Impulse is some sudden change in momentum. Well, this was very sudden. That arrow was accelerated very quickly. Why would this not be impulse? So impulse is a sudden change to a system's momentum, right? The system as a whole didn't have a change in momentum, right? If we look at, if it starts at 0 and then we take these final momentums and add them up, you'll still get 0. So there is no real change in the system's momentum, so it's not impulse. That's why it must be recoil. Okay? And the last question, does conservation of momentum, does con of mom apply? Yes, it does. The momentum was absolutely conserved in the system of these two objects, archer, arrow. Okay, good. Now, momentum being connected to Newton's laws. This is usually a GIF of these guys moving back and forth. It's a PDF now, so those aren't going to move. But number 1 asks us to use Newton's second and third laws to derive an expression for conservation of momentum. So let's start with Newton's second law. Newton's second law is F equals ma. Okay? We can modify F equals ma to show us information about momentum. So first, we will say that acceleration is the derivative of velocity with respect to time. So you could say F equals m times dv over dt, right? Now, a little trick in calculus. That d over dt, that can wander. Since everything is multiplied together using PEMDAS, right? If everything is just multiplied and divided, the order of multiplication and division doesn't actually matter. So we can move that d divided by dt around and say that f is the derivative d over dt of mv. Take that v out of the d dt. Now we know that momentum p is mv. So that can show us that F equals the derivative of momentum with respect to time. Okay? This is going to be very important. We'll actually talk about this later on in another video as well. But force can be shown as the derivative of momentum. Okay? And in our normal kinematic problems, we talk about force as mass times the derivative of velocity, right? Some changing velocity over time. That's what dv over dt means, okay? This means change in velocity, right? This means over time. Can't read that very well, can you? Let's fix that. This is a change in velocity over time. So we usually use some change in velocity over time for our kinematics. However, this equation shows us that you can also use constant velocity and a change in mass over time. So F could also equal dm dt times some constant v. And dm dt is change in mass over time. This is commonly done in physics problems where we have, say, a rocket is traveling at a constant velocity, but as it burns fuel, it has some dm dt of, some kilograms per second of gas, right, of fuel that is being used up in the rocket, but it's traveling at constant velocity. So that's a common problem that we use in physics to demonstrate this. And this right here goes to show you that that's true. The derivative of momentum over time being equal to force just shows you that you can take the derivative of mass or velocity as long as the other is constant. So that's our use of the second law. Now let's use the third law to bring this on home and finalize it with conservation of momentum. Whoops, let's change my marker thickness again. Let's use this one. So then we've got third law. Okay, third law is the idea that one force plus the other will actually equal 0 because F2 will equal the opposite of force 1, right? Third law is that every action has an equal and opposite reaction. So if F2 is negative F1, you're essentially saying that F1 minus F1 equals 0. Nothing controversial there, right? However, if we use what we just learned, we could say that F1 is the change in one momentum over time, and F2 is the change of a second momentum over time, and that would all equal 0, right? And that means that if some collision or some recoil is obeying Newton's third law, that this action really does have an equal and opposite reaction, then the momentums will also be conserved, meaning that if you add one is really just the opposite of the other. So that can prove, using Newton's second law and third law, that conservation of momentum is true. Now, number 2 asks what happens to conservation of momentum if an external force acts on the system, and compare this to conservation of energy. Okay? So when we have an external, let's say this is our system, right? Let's call this system. My penmanship's not good for that size of pen. So this is our system. If there is some external force, okay, external force acts on that system, then the momentum is going to change. Okay? Momentum changes. It can be increased, it can be decreased, but the momentum is going to change. Okay? And that is when momentum is not conserved. Okay? This is because momentum is either taken away or added to the system by this external force, because we can see that force can lead to a change in momentum over time. Right? Now, if we compare this to conservation of energy, right? Any external force, say if this were friction, we never used air drag in our conservation of energy unit, but if there were air drag involved, all of these things can actually take energy out of a system because there's some external force acting on the system. So again, if there's an external force acting on a system, you can also not only lose momentum, you can also lose energy. So the two conservation ideas that we've done so far are both affected by some external force. Right? Now we've got one recoil practice, and then we'll wrap this up. We've got these two blocks. Block M and 3M are on a frictionless horizontal surface. A light spring is compressed between them, and the cord initially connecting them is burned. So a burn on a cord usually means that it's going to have a clean break. If you cut it, then that means that there is possibly some tension. Like if the knife doesn't cut perfectly or the scissors don't cut perfectly, then there's some jostling of the objects. So that's why sometimes you'll see that a cord is burned in a physics problem. Immediately after the cord breaks, 3M moves to the right at 2 meters per second. So that would mean, let's call this V3 for 3M. That is traveling at 2 meters per second immediately after the cord breaks. what is the speed of m? We want v1. Okay. So if we're going, since it's frictionless horizontal surface, we'll say momentum is conserved. So they start off with zero momentum, right? They're attached to each other. Then all of a sudden you've got P1 plus P2. Well, we need P1, so let's subtract P2 to the other side to solve for P1. So you have negative 3m. Let's call that P3, so I don't get these things confused. Okay, momentum of object 1 and momentum of object 3. So that would be 3m times v3 divided by m would give you v1, right? So the m's will cancel, meaning that you would have negative 3 times v3, which is 2. So you've got negative 6 meters per second. And this is going to be negative because it's traveling to the left. Left is colloquially negative, whereas right is colloquially positive. So that's the speed of m, just using a quick recoil practice. Now, number 2, bumping up the difficulty a little bit. How much potential energy was in the spring if m equals 0.350 kilograms? So if that is the case, m equals 0.350, then 3m would equal 1.05 kilograms. And now it wants to know the potential energy in the spring. So what we can do is we can actually do a COE to solve this problem. If we have a COE, a conservation of energy, let's say it starts with the spring potential and they end with kinetic energies, and then you'll have a USF at the end, but that we'll say is at its ZPL. The spring no longer has potential energy to move the system. So we just spent spring potential. We don't want to separate that into 1/2 kx squared, so we'll say that this is spring potential equals 1/2 m v1 squared plus 1/2 3m v3 squared. And we have all of that information, so let's plug that in. US will equal 1/2, then we've got the mass is 0.35 times velocity of 1, which was 6 squared, plus 3m comes out to 1.05 times v3, which was 2, and we will square that. If you put that in your calculator, you come out to 8.4 joules of potential energy in the spring. So now that we've got conservation of energy, this can now just be a tool that we use. We've used the kinematic equations before. Okay, kinematic equations are kind of automatic at this point. We've also got F equals ma. That's just kind of automatic. You guys can do free body diagrams in F equals ma. Now we have a new method that is just going to become automatic and be incorporated in our problem solving conservation of energy problems. That method is now going to be new, and what we're going to try to do is add, whoops, oh no, here, let me make sure that that didn't mess up our stuff. Okay, so now we're just going to add conservation of momentum in this unit as a new method to solve physics problems. That's all we've got for this video on recoil. Next video, we will move on to impulse and talk about how that pertains to conservation of momentum.